Hi, I'm Sankalp. I'm an applications engineer at Maxim Integrated, and today I'm going to show you how to calculate the quiescent current of MAX17222 and how configuring the part properly can extend the battery life of your circuit. The quiescent current of the system comprises of the input quiescent current, the output quiescent current, and the transient protection quiescent current. First, let's calculate the input quiescent current or the total shutdown current. Now, the system's total shutdown current will depend upon the MAX17222 shutdown current and the current flowing through the enable pin. Hence, it depends upon how the enable pin is configured. Now, it is very important to note that the input shutdown current of MAX17222 takes into the account the leakage current of the inductor and the input pins. For example, if the enable pin is connected to the open drain GPIO of the microcontroller as in the figure, the input quiescent current of the system configured for an input voltage of 1.5 volts with a pull-up resistor of 33 mega ohms will be. Alternatively, the connection of the enable pin to a push-pull GPIO of a microcontroller using a push button, as in this figure, will result in a shutdown current of 0.5 nanoamperes. MAX17222 has internal circuitry which prevents the accidental shutdown of the part should the input supply rails dip below 0.8 volts, allowing the input voltage rails to go down to 0.4 volts depending upon the load conditions. Now, the extra current needed for the transient protection circuitry can be calculated as follows. For example, a part configured for a typical output voltage of 3.3 volts for a typical input voltage of 1.5 volts with a pull-up resistor of 33 mega ohms, as in this figure, where eta or the efficiency is estimated to be 85%. Hence, a part configured as will have a quiescent current of 767.7 nanoamperes, which is the sum of the input quiescent current, the transient protection current, and the output quiescent current. However, configuring the part as will have a quiescent current of 813.1 nanoamperes. Hence, to extend the battery life of the circuit, it is advisable to use a push-button configuration. Now, I'll demonstrate MAX17222EVKIT to you. Here, you can see I have connected the multimeter at the input to measure the input voltage and the input current, and at the output to measure the output voltage and the output current. I've connected the output of the EVKIT to a programmable electronic load which has been set to draw a fixed current of 6 milliamperes. Now let's turn the power supply on and see what happens. Now, we can see the input voltage is 1.5 volts and the part is drawing about a current of approximately 12 milliamperes, and the output voltage is a steady 3 volt for an output current of roughly 6 milliamperes. Now, let's check the transient protection feature of the part by turning the input voltage down. You can see the part is still working for an input voltage below 0.8 volts, giving a steady output of 3 volts and an output current of 6 milliamperes. Now, let's turn it down a little bit more to see if the part is still working. On turning the input voltage down a little bit more, we can see the part is still working for an input voltage lower than 0.8 volts. The best thing about using this part is that configuration of the output voltage is as simple as changing one resistor right here, that is R-select. Now, I'm going to change the output voltage of the EVKIT by changing one resistor, the R-select resistor. Now, changing the output voltage of the part is as simple as changing one resistor, which is R-select, which corresponds to R101 on the EVKIT. Now, I'm going to change it to 10 kilo ohm to get an output voltage of roughly 4.5 volts. Now, after changing the R-select or R101 on the EVKIT, we are trying to measure the output voltage, and you can see that we have successfully configured the part for an output voltage of 4.6 volts. If you want to find more about the product, see the link in the description below.